Assalamu alaikum, dear students. I'm very happy to be back again with another video lesson. In the previous video lesson, we were talking about that the angular speed of some of the things can be constant, like the clock's hands, like the second hand, the minute hand, the hour hand, and also the Earth's rotation and revolution. And then after that, we were talking about the angular acceleration. We said angular acceleration, it is the time rate of change of angular speed, and it was measured in radian per second squared. We said that if the angular speed does not increase or decrease, then the angular acceleration will be 0, because angular acceleration means the angular speed, it is either going to increase or decrease. So if the angular speed is uniform, if it is constant, if it is not changing, like the angular speed of the clock's hand or Earth's rotation and revolution, then we can say the angular acceleration is 0. And then after that, we solved some questions related to the angular acceleration. And of course, you know that angular acceleration is a vector quantity. And we also said that if, like during speeding up, the angular acceleration and angular speed will always have the same direction. But if the object is slowing down, the angular acceleration and the angular speed will always have opposite direction, regardless to whichever the direction the angular speed is, whether it is clockwise or counterclockwise. And then we ended right up at this point here. And now today, or in today's lesson, we're going to kind of like compare the quantities that we had in grade 11, or the linear quantities, with their substitute or equivalence, let's say rotational quantity. So this is the thing that we have. So we're going to start with this one here. We said last year, of course, you remember in grade 11, we had, let's say, these linear quantities here. Of course, for displacement, we had, let's say for displacement, we had x here. But this year, of course, for angular quantities, we have, let's say, angular displacement. Last year, we had velocity. Let's say this year, we have angular speed. Last year, we had acceleration. This year, we have angular acceleration. But we also last year had the 4 equations of motion, you could say, or the 4 kinematic equations. Do we have the 4 kinematic equations in rotational motion? Yes, but remember, first we have to make some changes. So first of all, I'm going to write the 4 equations or the 4 kinematic equations, and then after that, we'll make the changes and then rewrite them one more time. So if you remember, the 4 equations that we had, the first equation was, let's say, V final was equal to V initial plus acceleration delta t. That was the first equation. And then the second equation, of course, this order can change, but the 4 equations are always the same here. So we said delta x, that's what we had, is equal to 1 over 2 V initial plus V final delta t. That was the second equation. The third equation was delta x again, V initial, delta t, plus 1 over 2 acceleration delta t squared. And then the fourth equation, it was V final squared, yes, V initial squared plus 2 times acceleration delta x. That is what we had last year. But remember this, we said these are for linear, you can say, motion. And we said we're going to make these changes here. So these are, you can call them the kinematic equations for translational motion. Right? Remember, we're going to make these changes. We're going to write, instead of, let's say, every delta x, we're going to write delta theta. Instead of every velocity, we're going to write angular speed. And instead of every acceleration, we're going to write angular acceleration. So let's rewrite them and see what will they become here. So the first equation that we have, it becomes, remember this, instead of final velocity, it becomes final angular speed here. So we'll say omega final, it is equal to omega initial, right, plus we can say angular acceleration delta t. Very good. That is the first. What about the second one? Instead of delta x, we'll write delta theta, 1 over 2. Instead of V initial, we'll write omega initial, and then omega final delta t again here. All right, now third equation becomes delta theta again, because instead of delta x, instead of v initial, we have omega initial delta t plus 1 over 2. Instead of acceleration, we have angular acceleration delta t squared. And then the fourth equation would become, instead of v final, we have, or it would become omega final squared, don't forget, omega initial squared plus 2 times angular acceleration delta theta here. So these are the 4 kinematic equations in translation, and these are the 4 in rotational motion, you can say. Rotational motion, you can say. All right, now you might wonder, like, how do I know when to use these equations, or which equation should I use specifically when it comes to a question? Well, first of all, before you decide which one, you have to memorize the 4 equations. And how do you memorize them? If you're just gonna, for example, like revise, it's not gonna be easy. So the best method to memorize these 4 equations is to write them on a paper, maybe 10 times, 15 times, 20 times, and then you'll see that soon after you start to memorize without doing a lot of efforts, let's say. Now, to answer the question, the next question is, like, which equation do I use, let's say? That depends on what is given and what is required in the question here, but there's always a key. If you've noticed so far, we have 5 variables here, and those variables are, we can say delta theta, we have omega initial, we have omega final, and then we have angular acceleration, and then there is delta t as well. So there are 5 variables that can change. If we've noticed so far, in every equation that we have, there's always one of those variables are missing here. So if you take a look, or if you look at the first one here, you will see that angular displacement is missing in this equation. So we'll use this equation, or the first equation, if delta theta is neither given nor required. What does this mean? That means if the question does not give you information about angular displacement, and it does not ask you to find angular displacement. So that is when we say it is neither given nor required. Okay, what about the second equation? Have you noticed? As you can tell here, angular acceleration is not in this equation. So if angular acceleration is neither given nor required, then this is the equation you need to use. What about the third equation? You notice, so omega final is, you can say, missing in this equation. So if omega final is neither given nor required, this is the equation you need to use. What about the fourth equation? You can see that delta t is missing in this equation. So if delta t is neither given nor required, then this is the right equation to use. Okay, so this is regarding to this one here. Now I'd like to repeat this one more time. Remember this, okay? Now, remembering, or let's say go back to the linear quantities and the angular quantities, we said in grade 11, okay, we had delta x. And what is delta x? That is clearly the displacement, you can say. So let me just write delta x here. Delta x, of course, it was the displacement. We'll just write it. All right, and it was delta x. And delta x, it was measured, like the SI unit for delta s was meter here. Delta x, that is angular displacement. Why do I feel like I said delta s? Okay, so delta x, that is the angular, after the translational, you could say displacement here. But for grade 12, this year, okay, instead of displacement, we have angular displacement. An angular displacement, it is represented by delta theta. And how do we find delta theta? One more time. So delta theta can be found using arc length divided by the radius. We know that delta theta, or angular displacement, can be measured in radian, revs, or even in degrees, let's say. But only radian is allowed to be used in calculation here. And this one is also can be measured in meter, centimeter, kilometer, but the SI will be meter. The second thing that we had it was velocity here. So velocity can be found by using change in displacement divided by the time, and it was measured in meter per second. It was measured in meter per second. That is, you can say, the SI unit here. Okay, what about here for rotation? Let's just make this one number 2. Instead of velocity here, we have angular speed, remember, and it can be found by using delta or angular displacement divided by the delta time here. And angular speed, it is measured in radian per second. Can also be measured in other units as well, like revs per second, revs per minute, could be even degrees per minute, doesn't matter. But this is the unit that you have to use in calculation. And then the third thing that we said last year, we had acceleration, which can be found by, let's say, using the change in velocity divided by the time. If you don't have the change, you can say V final minus V initial over delta T. Well done. Acceleration was measured in meter per second squared. But this here, because we're dealing with angles, so we have angular acceleration. It can be found using change in angular speed divided by delta time. Well, if we don't have the change in angular speed, we can say omega final minus omega initial divided by delta time. And what is the unit of angular acceleration? This one was meter per second squared. So what do you think about this one? It has to be radian per second squared. So once again, these are, we can say, the linear quantities, and these are the angular quantities that we'll be dealing with this year. All right, now let's start solving some questions perhaps. Okay, so remember, these are the linear and angular quantities, and these are the 4 equations, but remember, in linear motion, you can say with constant acceleration. The other side would be in rotational motion. Okay, remember, rotational motion, you can say, only applies for objects that are rotating, let's say, about a fixed axis. Don't forget, and also, the acceleration must be constant. If the acceleration is not constant, then you cannot use these 4 equations. The second question, basically the second point, it says the question's information tells you which equation you're supposed to use. And we just talked about this one, linear quantities and how they can be found, and also their angular quantities, how they can be found, and also their units as well. So here we have a Wozzetti question. What does it say? It says, which of the following rotational equations is incorrect? Make sure you see incorrect the way that is written, so that, because due to the lot of pressure and stress, you might not see that. You might just see that it says there's a correct or whatever. So the first equation you see it is correct, you might just go ahead and write it. So which one is incorrect? Remember, this is the fourth equation based on the series, let's say, or the sequence that I wrote. So this one is totally correct. There's nothing wrong with this one here. What about the second one? You can see B, it is the second equation. Again, this one is correct. There's nothing wrong with this one either. What about C here? You can see that it's all correct, and that was the third equation. What about the last equation here? You see omega final, omega initial plus delta t, delta theta. Did we have delta theta in this one? This is clearly the first equation. We had angular acceleration delta t, or you can say delta t angular acceleration. So option D is incorrect. Remember that. All right, now we have another question here. Make sure, like when you go through the keywords, you underline every single keyword so that you know what is given and what is unknown, so that you can solve the question correctly. So this is one of the questions that we have. Says, the wheel on an upside down bicycle here moves through 11 radian. This 11 radian is delta theta, and you know that. That's a good thing. The second thing, it says it is in 2 seconds. So this is delta t that is given here. The question asks, what is the wheel's angular acceleration? So angular acceleration is unknown here. If it is initial angular speed, so this is omega initial is this much here. So take a look at what is given and what is not given here. So we have delta theta, there is delta t, there is angular acceleration required, and then omega initial is given. So have you noticed so far or not yet? omega final, or final angular speed, it is neither given nor required. So that, of course, leads us to use the third equation, because third equation does not have omega final in it. So in order to use the third equation, we have delta theta, it is equal to omega initial delta t plus 1 over 2 angular acceleration delta t squared. So what I have delta theta, it is 11 radian. It is equal to omega initial is 2. The time is 2 seconds plus, we can use a bracket here, all right, just so that we can separate this two. 1 over 2. Angular acceleration is required, and then times delta t, which is 2, but don't forget the squared. All right, so let's do this one more time. Now we have 11, it is equal to 2 times 2, that is 4, plus, and then 2 squared 4 with this 1 over 2, that is going to be 2 angular acceleration. We're going to move this 4 to the other side here. So 11 minus 4, right, it is equal to 2 angular acceleration. 11 minus 4, that is 7, equals to 2 times angular acceleration. Now divide both sides by 2. Of course, angular acceleration, let's just say 7 by 2, that is equal to 3.5. And the unit for angular acceleration is radian per second squared. This is how easy it can be. Of course, if you follow, like the question step by step, what is given and what is required. And this, you can see that this is a very similar question to, like if it's exactly, you can say that. Sometimes they'll change some numbers, sometimes it is exactly the same. So this is for you to practice. There's also a similar question like this been in Wizari, but what was different from this, it was this. Instead of giving you this initial angular speed, they were giving you final angular speed. And if they give you final, remember, you cannot use this equation. We have the question, inshallah, we'll get there soon. And then once we get there, we'll solve it. Okay, moving to another question, and that is this one. All right, it says a remote control car's wheel accelerate at 22.4 radian per second. If the wheel begins with an angular speed of 10.8 radian, what is the wheel's angular speed after exactly 3 full turns here? So let me tell you what is given here and what do you need to find here. Remember, it says it accelerates, so this is the angular acceleration. All right, it says the wheel begins with an angular speed. So can we say this is omega initial? Yes, well done. What is the wheel's angular speed? Are they asking for omega final? Yes, well done. But it says exactly after exactly 3 full turns. So that means delta theta, it is equal to 3 turns here. Now let me give you an idea regarding what is written here. And then whenever it says exactly after 3 full turns here, remember this, that every single turn, it means 1 rev. And I need you to remember this clearly. Okay, so one more time. Remember, this is the object that is moving in a circle. So here's, let's say there is a point right at this point. Every 1 turn, that is 1 rev, you can say. Remember, every 1 turn, that is 1 rev. What about 2 turns? That is going to be 2 rev. And 3 turns, it is going to be 3 revs in here. And of course, you know that every rev, it is equal to 2 pi radian. So one more time, let's write what is given and what is unknown so that we can get into this question here. Okay, so let's do that. Once again, so we have initial angular speed, which is 10.8 radian per second. And then we have omega final, it is unknown. So let's write it down. And then angular acceleration, it is 22.4 radian per second squared. And then the question says, or delta theta, it is 3 full turns, or you can say 3 rev, because every rev is 2 pi radian. Okay, so that is 3 times 2 pi, it is going to equal to 6 pi radian. Now, after having all this, look, what is neither given nor required here? Can we say delta time is neither given nor required? Yes. If that is the case, what equation are you supposed to use? That is the fourth equation. Well done. So the fourth equation says omega final squared, it is equal to omega initial squared plus 2 times angular acceleration delta theta. Is that true? Well done. So let's do that. What is omega final? It is unknown, right? So let's rewrite it. Omega initial, it is 10.8, but don't forget the squared, plus 2 times the angular acceleration, it is 22.4 times the delta theta. Okay, so remember, we said delta theta, it is 3 full term. Every term is, let's just write this. So we said delta theta, 3 term. Every term is the same as 3 rev. Every rev is 2 pi, so that is going to be equal to 6 pi here. Now all you have to do is just do this one, omega final, like 10.8 squared plus this much, and then you can find omega final. So let's find out what is omega final. It is equal to, so 10.8, don't forget that is squared, plus 2 times 22.4 times 6 pi. The answer is going to be, or it is going to equal to 961.1. 961.1, that is going to be omega final here. But we don't want this one. We want omega final not squared. I mean, how do we get rid of the squared? So we'll take the radical for both sides here. So now we can say omega final, the radical of 900 of this. Let's just use the radical of the answer. That is going to be 31 radian per second. This is how easily you can find omega final. Pretty easy. If you just follow what is given and what is unknown, then of course it becomes very easy. Okay, the next thing that we have, what does it say? It says, how long does the wheel in question 1 take to make the 3 full turns here? Well, we just added, let's say, or we just, let's say, found, let's get this one back. We have just found, let's say, we have just found the omega final in the previous question. So add omega final to what we already know, then you can find the time here. By adding this to what we already know, that you can easily find this one. You can use the first equation, by the way. What does the first equation say? It says omega final is equal to omega initial plus angular acceleration delta t, because we want delta t, yes? But if you rearrange this equation, you will get this one. The equation of angular acceleration, omega final minus initial over delta t. Do you know that? Isn't it easier if I just use this equation? Then in this case, delta t, it will give me, let's say, that is omega final minus omega initial divided by angular acceleration here. Angular acceleration. So what is final? We just found it was 31. What is initial? 10.8. And then the angular acceleration is 22.4. So let's just do the math and see what is it equal to. 31 point, actually it's right here. Okay, but we'll still do that. 31 minus 10.8, and then that is divided by 22.4. The answer is going to be 0.9, you can say. And of course, if you take some other digits, it will equal to 0.9017. By rounding, you can get to that is going to be in second, because this is the time here. This is how long it takes. Pretty easy. Of course, that is related to the previous question. Now, this question is also very interesting here. The first part is super easy. The second part can also be easy as well. So let's just go through this one here. But first, make sure you write the keywords. Okay? So, what are the keywords here? It says, scroll down a little, scroll down. It says a drill starts from rest. Now here's a keyword. Starting from rest, what does it mean? That means omega initial is 0. Well done. It says after 3.2 seconds, isn't this the delta t here? Yes, so this is delta t. Of a constant angular acceleration, the drill turns at a rate of 2628 radian per second. Can I say this is omega final? Yes. So if that is omega final, the first requirement says what? It says find the drill's angular acceleration. So how do you find the drill's angular acceleration? If you have initial and final, and then delta t. Well, angular acceleration, or finding angular acceleration at this point, must be very easy. So we'll say angular acceleration, that is again the same as the first equation, omega final, yellow, minus omega initial, divided by what? Divided by delta t. That's it. That's simple here. So once again, omega final is 2628. Or I said the opposite. Yes, 2628 minus initial is 0, and then divided by the time, which is 3.2 or 20 seconds, doesn't matter. All right, so now after doing this, of course, the angular acceleration would equal to 821.25. It is going to be radian per second squared. That is the first part of the question, finding the angular acceleration here. What about the second part of the question? It says, determine the angle through which the drill rotates during this period. So how do you find the angle that this drill rotates through this period? You might wonder, like, what can I find the angle in? Let's say, should I find the angle in degrees, in revs, or just in radian? Look, remember, delta theta, it is always in radian. Are they asking you, or are they saying find the angle in revolutions, or how many revolutions does the drill rotate? No. Are they saying how many degrees does the drill rotate? Again, no. So you have to find the angular displacement in radian here. Okay, so now we already found the angular acceleration. So how do you find delta theta now? Because you have initial and final and delta t, let's say, and you found angular acceleration, you can use any equation with angular displacement in it. That means you can use the second equation, you can use the third equation, you can also use the fourth equation, as long as, like for example, you have all the informations, which you do at this point here. So in order to find delta theta, but which one is the easiest? The second equation. Why? Because it doesn't require a lot. So we'll say delta theta, don't forget, it is equal to what? It is equal to 1/2 omega initial plus omega final times delta t. All right, once again, delta theta, it is equal to 1/2. What is initial? We said it is 0. What is final? That is 2628. What is the time? We said times 3. We should have covered this one here. Times the time, which is, what was the time? 3.2 seconds? All right, so now all you have to do, just do the math, and you'll find the angle, or angular displacement, which is going to be 4,205 radian. But here's another question. That is the answer at this point here. But what if the question we're asking, how many revolutions does the drill make during this time? Then, of course, at this point, it would have just divided by 2 revs here. And that's it. 2 pi, my bad. This is in radian, how do we convert radian to revs? Just divide by 2 pi. What if the question we're asking, how many degrees does the drill rotate? In that case, you could have just multiplied by 57.3, because if we want to convert radian to degrees, then you can just multiply by 57.3, and you would have gotten the answer right here, or you can get the answer. So you can always try different ideas, even if they're not asking for. Not in the exam, just for you to practice. Now here's this question. I really like this question, right? Because it's interesting. So what does it say? It says the tub within a washer goes into a spin cycle. So of course we have washing machine. So there has this tub, this let's say cylinder that you put the clothes, in, and then once you turn the washing machine, it starts to rotate. So that is what they're talking about here. It says it goes into a spin cycle, it starts spinning, but it says it is starting from rest. I want you to underline these keywords here. Starting from rest, that means omega initial is 0. And then reaching an angular speed of 11 pi radian. So we can say this is omega final in 8 seconds. Okay, so initial, final, and delta t here. It says at this point, what does it mean at this point? That means at this speed here, it says the lid is open. Okay, sometimes if you try to open the washing machine, it has a lid, right? So you do that well, a lot of washing machines, like will be locked once it is working. But just in case, for example, if the lid is open, then the washing machine like immediately starts turning the, let's say, or the washing machine goes off so that, nothing bad would happen. So it says the safety switch turns off the washer. That's what happens here. So it says the tub slows to rest. What does it mean, slows to rest? That means omega final, it is going to be 0, but in what time? In 12 seconds here. But you might say, how am I going to understand this? There is omega initial, final, delta t. There's another final, there's another delta t here. So how would I know? I'll tell you the method here. But here's a question, it says, through how many revolutions does the tub turn? So find delta theta, but not in radian, in revs here. How many times does it revolve while the washing machine, for example, let's say during the starting on, let's say the slowing down or turning off here. So the easiest method to do this is this one, which I would recommend to you here. Always when it comes to this, all right, so let's redo this one here. But first, let's just say this is the washing machine. It is starting from 0, okay, and then it is going to, I think this one I should have drawn a bit here. So this is what we have, the washing machine. Wow, okay, so here's the washing machine, let's say, or you can say this is the starting point here. So at this point, we can say this is omega initial, okay? Starts from 0. And then after that, it is going to speed up until it becomes, for example, or reach, let's say a final angular speed, which is going to be 11 pi radian here. And then from this point, it is going to slow down until it stops here. Okay, let's just do this one here. So now, at this point, it says at this velocity is going to slow down until it becomes what? Until it becomes 0. So now that means the other omega final is going to become 0. But from what angular speed is it going to slow down? The question says at this point. So starting where we can see that from 11 pi radian, it is going to slow down. So 11 pi radian for this path, or for this part, it is going to become what? The omega initial for this part. But let's not forget, how long does it take to speed up to get into, let's say, 11 pi radian? It takes 8 seconds. And how long does it take to slow down and stop? It takes 12 seconds here. This is exactly what happened. Now you can, name these parts. You can say here, speeding up here, right? Speeding up. Here you can say slowing down or stop working here. Here you can say starting to work. Here is going to slow down, all right, until it stops here. Okay, now if you've noticed, these are the omega initials and finals that is given here. So in order not to get confused, why do we have, for example, 2 finals and 2 delta t's? This diagram would help you a lot in order to understand the question. Once again, starting from 0, it is going to speed up until it reaches 11 pi, that is omega final. From this, or at this point, it is going to slow down. So now for slowing down, omega initial becomes 11 pi because it slows down from this point until it stops, so omega final is 0 here. How long does it take to speed up? 8 seconds. The time it takes to slow down and stop is 12 seconds here. Now, if you've noticed, angular acceleration is neither given nor required, even though it says the angular acceleration is constant while speeding up and slowing down. So here's a question. How do you find delta theta, but in revs, don't forget? Now, we can start with this. We can say for speeding up, delta theta, once again, angular acceleration neither given nor required, so we'll use the second equation. So angular displacement, delta theta, it is equal to 1 over 2 omega initial plus omega final delta t. That is for the first part. Once again, delta theta, 1 over 2. What is initial? 0. What is final? It is 11 pi times how long does it take? 8 seconds here. So once you do the math, you will get 44 pi radian. Now you can convert this one to rev right away, but I don't want to do that now. I want to find both thetas here, right? And then find the total. Okay, so I can call this one delta theta 1, that is for the first part. And then for the second part here, I can call it delta theta 2. I'll use the same equation because I have the same, let's say, circumstances. So angular acceleration is neither given nor required. So again, delta theta 2, 1 over 2, omega initial plus final, delta t here. So once again, 1 over 2, what is initial again? This time, initial is 11 pi because it starts to slow down from this angular speed, then until it stops, so final is 0. How long does it take? 12 seconds. So if you do the math, 12 divided by 2, 6 times 11 pi, that is going to be 66 pi radian here. So this is delta theta 2 here. Okay, so now, how do you find, for example, the angle that is the object is rotating but in revolution? So all we have to do, just add the two together and then we convert this to rev. So we'll say delta theta total, all right? That is, you can say delta theta 1 plus delta theta 2. So delta theta 1, it is 44 pi radian. Delta theta 2, it is 66 pi radian. That gives us a total of 110 pi radian. But once again, we don't want angular displacement in radian. The question says through how many revolutions does it rotate? If they were not saying how many revolutions, just find the angular displacement, you would have just stopped solving at this point here. But because they say how many revs, so you will just convert this rate into rev. And how do you do that? Simply by dividing by 2 pi. And once you do that, then delta theta in rev, it is equal to what? It is equal to 55 revs, and that'll be the correct answer here. Sometimes I would like to, actually no, I think that would be unnecessary here. Okay, so this is the answer here. What if they were asking through how many degrees does it rotate? Then at this point, you could have just, or you would have just multiplied by 57.3, and that'll be the answer. All right, I hope it was clear enough. Okay. All right, now moving next, and this is the solution here, but there's one thing I would like, perhaps I want you to do. Find a space here, and you can draw the diagram that I just did for you here. So starting from 0, that is, let's say during speeding up, omega initial is 0, final would be 11 pi radian. Okay, and then for slowing down, this side would be the initial, and then the final would be 0 here. Remember, for this part it takes 8 seconds. For slowing down, it takes 12 seconds here. Because this diagram would help you understand the question and solve the question way easier. Now we have another question which is also interesting here. It says a coin with a diameter of 2.4 centimeter. And the only purpose of diameter being given is so that we can use that to find the radius. So at any point, if diameter is given, you can use the diameter to find the radius. Okay, so here's what we have. A coin with a diameter of 2.4 centimeters dropped on a horizontal surface. So let's see what is given and what is unknown here. This is the diameter. It is 2.4. Don't forget, you have to convert centimeter to meter. It says the coin starts out with an initial angular speed. So this is omega initial. Don't forget. Okay, it says on rolls in a straight line without slipping. If the coin or if the rotation slows with an angular acceleration of magnitude, we know that whenever an object is slowing down, the acceleration will always be negative, let's say, because that'll be opposite to the velocity, no matter which direction is the velocity is. So at this point, we'll just say it is negative. So here's the angular acceleration. We can say it is negative 1.9. Why? Because the question says slows down. If the question were saying speeds up, then you would have used the same number, a positive number. But look, the part that is the most important here, the question says how far does the coin roll here? Does it says what is the angle that the coin roll? No. Does it says how many revolutions does the coin roll? No. Does it says how many degrees? No. So whenever we have questions, let's say angular quantities like this, and the question says how far, and by the way, that is the only question that we have at this point. Whenever it says how far the coin rolls, remember they want the distance that is traveled. And what quantity tells us the distance that is traveled? That is the arc length, don't forget. And I'll tell you why in a second. But if we continue with this, it says before, like the coin roll, before coming to a rest. Coming to a rest, that means omega final is or will equal to 0. And that is as simple as this one here. So how about we do this one here? Okay, so first of all, let's just bring this one back and answer this question, see how much, okay, or how far is it going to roll, let's say. A little, all right. So first of all, let's write what is given and what is unknown. Once again, the first thing that we're given is the diameter, yes? What is the diameter? It is 240. Okay, 240. How about we just find the radius at this point? We'll just say the radius that is equal to the diameter divided by 2. So 240, all right, 2.40 divided by 2, that would be 1.20. But don't forget, this is in centimeter. How do you convert in meter? Divide by 100. Then the radius is going to be, or it is equal to 0.012 meter. That is the radius. Okay, of course, you will need this. And then the second part that we have says an initial angular speed. So omega initial is 18, you could just say 18 here, 0.0, no need to do that, radian per second. And then we have the omega final. It says coming to a rest, that is 0. Angular acceleration, we said because it says slowing down, it is negative 1.9. And then the question says, how far does it roll? Remember, because the question says, how far does it roll? That means the arc length. But where do we find, or where can we get the arc length? If I have delta theta, we know that. We can get it from the delta theta, which equals to arc length divided by the radius. But before finding the arc length, I need to find the angular displacement. Up to this point, you've noticed we have initial, final, angular acceleration, and now delta theta is required. So is delta time, is it either given, let's say, or required? The answer is no. So what equation do you think we should use? The fourth equation. Yes, and that is the correct one. Well done. So we'll say, let's use this color maybe. So we'll say omega final squared, that is equal to omega initial squared plus 2 times angular acceleration delta theta. Once again, I need to find delta theta so that I can find the arc length. Okay, perhaps one more thing that you might need to know is this maybe. Consider we have, let's say, this is what I mean, or why we need to find the arc length here. So this is the coin that is rolling down here. This coin, once it is rolling, of course, it is going to cover or travel a certain distance here. But this certain distance, of course, how far it goes depends on what is the arc length that the object is, let's say, or that would be equal to the arc length, for example. Now, if we start at this point here, now this coin is going to roll here, of course. So how much it is going to roll, this is the arc length that is going to travel. So this straight line, or how far it is going to be equal to the arc length of this coin here. Okay, so now let's get back to what we have just started with. All right, so let's get rid of this one here. So going back to this, omega final says 0, 0 squared, still 0. Omega initial is 18, but don't forget the squared, plus 2 times the angular acceleration, we said it is negative 1.9 times delta theta here. So once again, this 18, of course, we can take to the other side, or if not, it would be better or easier to move this one. So let's just write one more step. I'm extending this one so that you can understand what happens here. So 0, it is equal to, what is 18 squared? 18 squared, it is equal to 324 plus and minus, of course, 2 times 1.9. 2 times 1.9, that is, of course, it is equal to, we can say, wow, 2 times 1.9, the answer is going to be 3.8. So minus 3.8 delta theta. Now this part is negative. Can we move this one to the other side? Yes, that'll be positive. So we'll say 3.8 delta theta, that is equal to 324. Now how do you find delta theta? Just both sides divide by 3.8, or if not, you could just take 3.8 to this side. So this cancel out. We can say delta theta now, what is it equal to? 324 divided by 3.8. So the answer is going to be 85.26. 85.26. What is the digit after 3? So we're just going to leave it here. But remember, this is the delta theta, which is in radian. But we don't want delta theta. We said we want the arc length. So once again, delta theta, it is equal to the arc length divided by the radius. Cross multiply, arc length, it is equal to delta theta times the radius. So what is, one more time, the arc length, it is equal to, what is delta theta? We said 85.26 times, what is the radius we just found? In meter, it is 0.01. Seems we're out of space. Okay, so let me just bring this one a bit closer. So 85.26 times 0.012, okay? So after you do the math, let's just say multiply by 0.012, the answer is going to be equal to 1 point. So we'll say the arc length, that is equal to 1.02315 or whatever. I think we'll just write up to this point. Even though these are a lot of digits, you could have just wrote 1, that would be fine. And this is, of course, is going to be in meter. This is how far the coin rolls given the circumstances that we have. And by the way, I would recommend you always try to reverse the questions here. And what do I mean by reverse the question? Now consider you have the arc length and you have the radius. You can use this too. This is just like work in the opposite direction here. I mean, starting from arc length here, with the radius you can find delta theta. If you have delta theta, you can use this in the, let's say, for equations of motion, or this equation, the fourth one specifically, to find out whichever of those, if they are unknown here. That is something called reverse process, and I'm sure if you do that, you'll benefit from this a lot, inshallah. So, and that is the answer, of course, which is about, you could say, arc length that is traveled, it is by the coin, it is going to be 1 meter. Now here we have another question. This question is exactly the same as the other one, but there is one thing, actually, there's one idea I want you to be aware of, otherwise there's nothing much. It says a mass attached to a 50 centimeter string starts from rest. Starting from rest, that means we can say omega initial is 0. Let's make this one, or use the color here. Okay, so that means omega initial is 0. That is starting from rest. You can even say V initial if you are not sure, 0, because it doesn't matter. Up to this point, we don't know if it is rotating or if it is moving in a straight line. So, but if it is 0, it doesn't matter. And it says rotated in a circular path. Now, if it is a circular path, we know that it is rotating, so you can erase this one here. It says exactly 40 times. Okay, we've mentioned earlier that every time an object is moving in a circle, isn't that 1 rev? So if it is going to rotate 40 times, that means every time is basically 1 rev. So that means the object is going to rotate 40 revs. But we know that every rev, it is equal to 2 pi. So 40 times 2 pi, that is a total of 80 pi. And this is the angular displacement that is traveled or covered by the object. It says in 1 minute. Clearly you convert the minute, or you have to convert the minute, right? by multiplying this by 60 seconds before reaching a final angular speed. So what is the angular speed? What is omega final? So again, we have initial, we have delta theta, and we have the time. Which equation to use? We're going to use the second equation. Why the second equation? Because angular acceleration is neither given nor required. So the second equation would be the best. Delta, or delta theta, or angular displacement, it is 1 over 2 omega initial plus omega final delta t. And then once again, delta theta, it says 40 revs, which we said that equals to 80 pi, yes? Well, then that is 1 over 2. Initial was starting from rest, means 0. Final is unknown. How long? In 1 minute, which is equal to 60 seconds. Okay, so now you can simplify this too. 60 by 2, that is going to be 30. And then we can say 80 pi, that is equal to 30 omega final. So how do you find omega final? Now you could divide, of course, both sides by 30 if you want to. So that is going to be 80 pi divided by 30. Then do the math, you will find omega final, which is going to equal to 8.38 radian per second. And this is how you can find omega final. Pretty simple. Okay. Remember I told you there was a question where instead of giving you omega initial, they're giving you omega final, and that is this question here. It's a bit tricky, so don't fall for this one. And let me tell you what is the trick about. First, let's go through the question. It says the wheel of, or on an upside down bicycle, like the wheel of this bicycle that is upside down, moves through 10 radian in 2 seconds. So 10 radian, that is the angular displacement, right? So that is angular displacement. And then in 2 seconds here, so this is delta t here. These are given. What is the wheel's angular acceleration? So that is unknown. If it is angular speed, becomes 8 radian per second. And that is what I need you to be aware of. If you're not aware of this one, you might just say this is omega initial, and then of course, your 2 mark would just gonna be wasted here. Look, right? Of course you know English. It says the angular, if it is angular speed, becomes, which means that it was not this much, but now it is going to become this much. So this is clearly omega final. All right, if that is omega final, then how do you find the angular acceleration here? So let's do this one together. So once again, we said omega, once again, let's say angular displacement, it was 8, right? The time that was given was 2 seconds, okay? And then what is given was, all right, omega final, and it was, I forgot the number. The irony, man. Okay, so that is 8, and then the other one was 10. What a surprise. So this was 10, okay? And this one becomes 8 here. So remember, the question says, what is the angular acceleration here? Don't forget, right? Because, like I said, if you're not aware of this one, if you use this one as omega initial, let's just say you thought of this as omega initial, then you will say, I have delta theta, I have omega initial, I have delta t, I can easily find angular acceleration, and you will just start with the third equation, which is omega initial delta t plus 1 over 2 angular acceleration delta t squared. But once again, remember, if you're not aware of that, you're just going to use this equation. But now you can't. Why? Because in the third equation, you need omega initial, but what you're given is omega final. So what can you do at this point if you don't have omega initial? If you've noticed or not, out of all the 4 equations, let's say every single one of them needs or has omega initial in it. So that means it is a must for you to find omega initial. So how can you do that? Well, first of all, because the acceleration is unknown, how about, for example, if I want to find omega initial, what equation can I use? If you start with the first equation, you need acceleration, so you cannot. How about the second equation? The second equation would be the best, which says delta theta that is equal to 1 over 2 omega initial plus omega final delta t. Again, why are we using this? To find omega initial. Because if I find omega initial, all my problems will be solved. So does your problems. Okay, so delta theta here, it is 10. It is equal to omega, or let's say 1 over 2. Omega initial, it is unknown. Omega final, it is 8. And then the time is 2 seconds here. Now, you can simplify this to here. So 10, it is equal to omega initial plus 8. Take the 8 to the other side, it becomes negative, right? So 10 minus 8, it becomes omega initial. So we can say omega initial, it is 2 radian per second. That is omega initial. Now at this point, you can use, to find omega final, you can use the first equation, you can use the third equation, you can even use the fourth equation now because you have everything you need to. But once again, to find the angular acceleration, what is the easiest equation? It is the first equation. And if you rearrange the equation, or if you use the equation of angular acceleration, it is even easier. We know that omega final minus initial over delta t. Isn't that the equation for angular acceleration? So why do you have to bother go use the first equation and rearrange? Once again, if you rearrange this one, that's exactly the first equation out of the 4 equations, let's say. So omega final, we said it is 8, all right? Omega initial, we just found it was 2, and then divided by the time, which is 2. And of course, you might just simply divide the 2, and you would say 8. And of course, you will see 8 in the options, and you said, haha, I got the answer. But that is wrong, Kaka. Look. There is a negative in between the two, so you can never, ever cancel out these two terms. You don't do that, okay? So if you were one of those who thought you could just do that, you really got to worry about this. But if you already know this, well, congratulations. All right, so 8 minus 2, that is going to be 6 divided by 2, that is going to be 3. But what is 3 now? So the angular acceleration is 3. It is going to be radian per second squared, don't forget, and that is your answer. This is why it was interesting. Once again, if you don't underline the keyword, you will fall for this. Make sure you're not one of them. Okay. Now you can see there's another question. One of my questions, you can give it a try. It's nothing complicated. Now we're almost like done with the first section, but there are a few questions. Let's go through these questions real quick. The first one says, convert the following angles in degrees to radians here. Now we've learned there are 2 methods to convert, let's say, angles from one form to another. One of the easiest one, if we want to convert degrees to radian, we could simply just divide by 57.3. If not, you could use the other method, which is exactly fine or the same here. So at this point here, you can notice that, for example, previously we were using 2 pi over 360. I've used, let's say, pi over 180. Makes no difference. You're just like simplifying this one here. So whether you use 2 pi over 360 or 1 pi over 180 makes no difference. As a matter of fact, you don't even need this one. Just make sure you divide 35 by 57.3, then this is the angle that what you get. What about the next one? You do exactly the same. 128 divided by 57.3, you'll get the answer in radian, and that's it. All right, what about this question here? We've solved questions like this, but I'll still give you the idea how you can solve this one. It says a mosquito lands on the phonograph record, which is 5 centimeters from the record center. Whenever there is a question tells you this much far from the center, that is always the radius, don't forget. So what did I just say? Whenever it tells you there is something here this much far from the center, that is always the radius of the object here. But you, of course, you have to convert the centimeter to meter. So if the record, it says turn clockwise or turns clockwise, so that means the arc length is going to be negative, delta theta is also going to be negative, but radius is always positive, don't forget. So the mosquito travel along an arc of length. So once again, this arc of length is going to be negative 5 centimeter. What is the mosquito's angular displacement? Delta theta. We've learned that delta theta, it is equal to arc length divided by the radius. Once again, now because I have this two both together, the arc length it is 5 centimeter. And we said because it is clockwise, so negative, and then the radius is also 5 centimeter. Because these are both centimeter, I don't have to convert. Because even if you convert, the units will always cancel out. So it is the same as if you haven't here. So 5 divided by 5, that is just going to be 1, but don't forget the negative. So angular displacement is going to be negative 1 radian, and that's it. Okay, that is the answer for the first question. What if they were saying, what is the angular displacement in degrees? You multiply this by 57.3. Then you get that in degrees. If you want to convert it in rev, just divide by 2 pi, you will get the answer, and that's it. So these are, just in case if they were asking for another thing there. But don't forget the negative because it says clockwise. Now here's this question, which is also very interesting. It says a bicyclist rides along a circular track. I think we've solved a question like this. If the bicyclist traveled around exactly half the track in 10 seconds, so what is the average angular speed? We've previously said that, for example, one full track or one full cycle, that is going to be what? That is going to be 1 rev. Is that true? But this question says half of the track. Half of the track, isn't that means half a rev? Yes, and half a rev is, what if it says quarter of a track? That'd be 1/4 of a rev. What if it says 3/4, let's say, of a track? That is going to be 3/4 of a rev. But here at this point it just says half a track. So it is going to be half a rev. That is 1/2. Every rev is 2 pi. So the 2 and 2 cancel out, which is going to be 1 pi radian. That is delta theta, don't forget. In what time? In 10 seconds here. So what is the average angular speed? We know that average angular speed, it is equal to, you can just say omega, it is equal to delta theta over delta t. So that is, we can say just pi, all right? If not, if you like, you can use 3.14, that is also fine, divided by 10. That is going to be equal to 0.314 radian per second. This is the angular speed in here. But there is also another question that I might ask you, for example, or add to this one here. What if, how about if, try to solve this question for yourself, just as practice, okay? See if you can get the answer right. We'll say, an object. Let's just see if we can do that. An object is traveling let's say traveling twice its radius in 10 seconds. What is the angular or average angular speed of the object? I should have said travels on a circle, traveling on a circle. On a circle, let's say, that's not even grammatically correct, but you get what I'm writing here. So an object is traveling, or let's say moving in a circle, and it's traveling twice of its radius. I think it would be best if I rewrite it. Okay, so let's just erase this part. An object is moving in a circle. An object is moving in a circle, and it's moving in a circle. In a circle. And then is traveling. And after that, it gets back to this point here. Okay? And is traveling twice its radius in 10 seconds. What is let's say it is average angular speed. Okay, now pause the video and see if you can solve this question. Look, so what exactly, or after, I hope you got the answer correct. If not, just let's just do this one here. So here's an object that is traveling on a circle. Okay, no matter what the radius is, the object is going to travel twice its radius. So let's say this is one radius and this is twice the radius. We don't care what the radius is exactly. But the question says, what is the average angular speed? So you will always start with what they're asking for. So the first step is, you can write what is given. If not, we'll just start with this one here. Average angular speed, it is equal to angular displacement over the time. So what is the time given? It says 10 seconds. Okay, but do we know the angular speed here? The answer is no. But can I find angular speed? The answer is yes. Angular speed, it is equal to the arc length divided by the radius. But if you've noticed, I said the object is traveling twice its radius. Traveling, when it says traveling, isn't that the arc length here? Yes, so I can say now, this arc length, it is equal to what? It is equal to twice its radius. Can I say 2 times in this case? Twice, whatever the radius is, this distance here is going to be 2 times that radius here. So instead of the arc length, we'll just write 2r. So now this 2r cancels out. We can say delta theta now, it is equal to 2 radian. Now, of course, after finding this one, you could just divide this one by 10. So that is going to be 0.2 radian per second. And that is the angular speed, just in case, Yanni. Normally, this question is asked when, like when we study angular displacement, we'll just say, for example, if an object is traveling, let's say twice its radius, what is the angular displacement? If it is only asking for angular displacement, twice its radius, like we said, let me just add one more step here. So arc length divided by the radius. If the question says twice its radius, that means 2 times the radius. That'll be the arc length divided by the radius. These two cancel out, regardless to whatever the radius is, and then the angular displacement will equal to 2. But if the question is about angular speed, then of course you'll bring this number to the equation, then you'll just do the math. And I hope you understood this question well. Okay, so the next question that we have regarding this one, so you knew, for example, how we could do this one. The question, of course, could change, let's say, from half a track to quarter of a track or 3/4 of a track, but you always know one track is one wave, which is 2 pi. If it is half, it'll just make everything half, and that'll be it. Regarding this one here says, or this question, it says, find the angular acceleration of a spinning amusement park ride that initially travels at this much. Initially travels, this is omega initial, then accelerates at this much. But don't forget, Baba, when it says accelerate here, the number right after accelerate does not necessarily mean this is the acceleration. So always double check with the unit of the number that is given. What do I mean here? If you're not careful here, you just because you see accelerate and there is a number here, you might just think of this as the acceleration. But if you look at the unit, here it says 0.6 radian per second. Is this the unit of acceleration? No. And do you know that, as a matter of fact, when something accelerates, it means speeds up to. So here's the accelerates here, it means just speeds up. Okay, so don't forget this. From this speeds up to this much, and always double check with the numbers here or with the unit of the number that is given. So this is omega final. It says during this much time, so this is delta t interval. So find the angular acceleration. So angular acceleration, you know that omega final minus omega initial divided by delta t. You have the final, which is 0.6, you have initial 0.5, and then you have the time, which is 0.5. Just do the math, you'll find the answer. And then there is another question here, says, what is the instantaneous angular speed? And that one is, perhaps this word might be a bit new here. When we say instantaneous, that means the velocity or the angular speed at that instant here, okay, or at that moment here. Angular speed of a spinning amusement park ride that accelerates from, once again, it says accelerates from, so this is the angular speed that it starts with. So this is omega initial. It is not acceleration here. And you can always tell by the unit. At a constant angular acceleration, but look, this time we have angular acceleration for 1 second. So it starts with this. After accelerating with this much, after 1 second, what would be the velocity? What is the instantaneous, what is the, let's say, angular velocity at that moment after this takes place? So clearly they're asking for omega final. Once again, we have initial, we have acceleration, delta t, omega final is unknown. So which equation are you going to use? The first equation, because angular displacement neither given nor required. So we'll just write the equation. Angular acceleration delta t. You have initial, which is 0.5. You have angular acceleration 0.2. You have the time 1 second. Just do the math. You'll find angular or final angular acceleration, and that would be it. All right, and give it a try. Solving these questions as well. That is the end of section 1.1. I hope you understood very well. If not, please make sure you go and review this one more time. Practice all the questions. All right, now one more time. Let's just, very quickly review what we went through today. We said we had the linear quantities, let's say, and then the angular quantities. Instead of, instead of displacement in linear or translational motion, we have angular displacement, which is delta theta. Instead of velocity, we had angular speed. Instead of acceleration, we had angular acceleration. And then, of course, we compared the 4 equations or the kinematic equations for translational, and then we did that for rotational, and then we started solving some questions. And then make sure you practice what you have studied so far, because there is this quote, practice makes perfect, but I believe in your efforts. So make sure you practice this often so that you don't forget. What is the next thing I wanted to say? Yeah, I think that's more than enough. Just take care of yourself, keep practicing. I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.